Hello everyone and welcome to today's webinar. Let's start with a quick introduction. My name is Laura Denzer and I'm one of the project managers at MeKo. Our expert today is Roman Böttcher from the head of production team, leading programs across stainless steel, cobalt, chromium, precious metals and polymer parts. In this session, we'll focus on laser welding for microassembly, how it works and how we use it to support your individual projects. Here's how we structure our time today. We'll start with a general overview of MeKo MedTech to give you some background, then move on to the main topic, laser welding for microassembly, and finish with questions and answers. So before we dive into the details, let's take a moment to look at what drives us at MeKo, our mission. Safe, innovative, and affordable. These three words define how we approach producing components for medical devices. They guide the way we work, how we think about quality, and how we collaborate with our customers to improve healthcare around the world. Our goal is to make medical technology better, more accessible, and more reliable, knowing that every component we produce plays a role in improving a patient's life. That's not just a statement on paper, it's the mindset that unites all of us here at MeKo. Behind this mission stands a strong team of more than 400 dedicated professionals, all working with passion, expertise, and a shared sense of responsibility. What once started as a one-man operation in a small garage has grown into a globally active company, committed to supporting our customers with high-precision components and dependable processes. Our company is ISO 13485 and ISO 9001 certified, as well as FDA registered, reflecting our commitment to the highest standards of quality in everything we do. But going further doesn't just mean supporting our customers with precision components. It's also about constantly evolving as a company, improving our processes, and exploring new possibilities for the future. Our research and development team contributes significantly to this progress, exploring, for example, new materials such as Resolloy, a magnesium alloy with exceptional elongation properties, polymedics, a high-precision polymer tube with integrated drug delivery, and Vasculoy, a nickel and cobalt-free alloy developed specially for patients with allergies. At the same time, we are refining our processes, expanding our capabilities in inspection and analysis, where our variety of existing measurement systems is further strengthened by the establishment of our new MedLab. This is planned to be certified according to ISO 17025, which is the international standard for testing and calibration laboratories. In addition, we also continue to drive automation throughout manufacturing and handling to make our workflows even more efficient and reliable. All these efforts come together in one goal: to build the foundation for the next generation of precisely manufactured components. To put this into practice, let's have a quick look at our general production flow. We typically start with laser processing, for example, laser cutting, drilling, or welding, then proceed to heat treatment, which is for nitinol, the primary shape setting to lock in the final geometry. Afterward, the parts are electropolished and cleaned. Finally, we passivate the surface to make it inert before every implant undergoes quality inspection. With that overview in mind, our focus today is laser welding for microassembly, how we achieve reliable, long-lasting joints for medical applications, and what other process expertise is involved. Before I hand over to Roman now, I want to remind you of the Q&A panel. Feel free to drop your questions there. We'll answer as many as we can at the end.
Hello, everyone. As Laura already said, I would like to speak about laser welding for microassembly. This is a joining technique for microscale components. If we are speaking about microscale components, we mean parts that have the lower dimensions in the micrometer or lower millimeter range. These parts are delicate because of their size, but they are often even more delicate. Think of thin wall thickness or structures that are cut or machined into them. You need high precision while assembling them to be able to fulfill the function at the end of the assembly, but oftentimes even to be able to do the joining process. These delicate structures are prone to be distorted, to be bent, for example, due to a heat input. So to join these components, it's very favorable to have a low heat input. You have to be careful while assembling them, but on the other hand, you also need very strong and reliable joints to fulfill the function of the components and to have a reliable medical device. We think that laser welding is highly suitable for this kind of application, and I would like to tell you why in the next couple of minutes. I would like to give you some technical insights, and I would like to show you some examples of what we do with laser welding. So let's start with some fundamentals. Welding in general is a joining technique. Their local volume of two joining partners is melted. The melted material of these two components or several components will blend. And after cooling down, a common weld is formed, which is permanent. It can't be dissolved independently from the other material. Filler material can be used as an option, but it's not that common for the type of laser welding we are doing for mechanical components. You need a certain energy to melt the material. It's in the range of 10,000 watts per square centimeter or 65,000 watts per square inch. But please keep in mind that's only a rough number because the actual amount of energy you need depends on the laser wavelength you use, the material, the geometry, and for laser welding, the mechanism for coupling the energy to melt the material is absorption, but not the complete energy of the laser beam can be used to melt the material. In the best case scenario, only 45% of the laser energy can be used to melt the material, and there are some losses due to heat conduction, or plasma shielding effects while welding. And of course, there are also losses in your laser guidance system from the laser source to your workpiece. There are different welding methods. Let's have a look at the left side of the slide at first. The first method is heat conduction welding. The laser beam hits the material will melt. If the laser beam or the workpiece moves, the material will cool down and form the laser weld in the fusion zone. For heat conduction welding, the penetration depth is low, but you will get a very smooth surface. Laser heat conduction welding is often used to smoothen the surface of laser welds that have been done with other welding techniques. On the right side, you can see deep welding. Here, the material will be melted as well, but due to a higher heat input, due to a higher energy input, it will also be evaporated. A plasma channel, a vapor channel will be formed that gets deep into the material, that gets deep into the joint, so that deep penetration depth can be achieved. The penetration depth can be in the range of 15 times larger than the welding width. The welds can be arranged in different styles. Let's start on the upper left side. The simplest form is that you put a single laser pulse onto the material, and then you will get a single weld spot. And you can set several weld spots on your joint to get more strength. You can even overlap your single weld spots. Then you will get a laser stitch welding. It looks like a seam, but it's not continuous, it's discontinuous. Laser stitch welding is the method we will use quite often because it's a good combination between strength and a low heat input. And last but not least, at the bottom of the slide, you will see an example for laser seam welding. There you will have a continuous laser energy along the movement along your joint so that you will get a full seam. Laser welding has a lot of benefits. Let's start with some technical benefits. These benefits are not only there for our medical application, but also for other applications. Think of food processing or pharma, where filtration elements are needed that has to be welded with a very clean surface that is easily cleanable, but also strong. And speaking of strength, that's typically the domain of mechanical engineering, automotive, and aerospace. For all these applications, you can use laser welding for a wide range of materials, metals, metal alloys, and even some polymers. We are able to process small parts and very big parts as well. The laser beam has a high power density focused on a small beam diameter, so you will get a small heat affected zone. You will get only low thermal stress on your joining partners, which results in a low distortion due to heat. Looking from the process side, laser welding has benefit that it's contact-free, and there are no tools that are getting in contact with your welding partners, with your components that are prone to wear. The process is well adjustable and it's repeatable. You can achieve high feed rates because you have high power density, which makes the process efficient. You will get good seam surface and seam properties, so oftentimes you can reduce the amount of work in post-processing. You will see an example on the right side of the slide. It's an example of an industrial application. What you see is a laser welding process of a spur gear from a manual transmission of a car. You have the spur gear and a cone that will be used for synchronizing the gears during shifting. Why is laser welding used there? All these components are already finished. The spur gear has a sophisticated tooth profile, and you can't afford to have a high heat input into these parts because you can't afford to have a distortion, a bending of the gear. Otherwise, you will have wear and reduction of efficiency during operation. There are a lot of benefits for laser welding. There are also some, let's say, requirements you have to meet. Your components that you want to join have to be precise. You can't afford to have a big gap between the components when you would like to weld them. With laser welding, you need a precise and reliable positioning system to position your part under the laser beam. And oftentimes you also have to plan your welding sequence very well to get accessibility to your welding position, but also to minimize heat input even further. You need a consistent laser source. And of course, every time when you're working with laser radiation, you have to have something that protects against this laser radiation. These are all requirements we are used to because we do a lot of laser welding and we have a lot of joy doing it. As Laura already said, we are able to manufacture components for you with different processes, and laser welding is one of them. We are a contract manufacturer, but we would like to be your solution provider as well, because we would like to give our know-how to you to help you to develop your components and bring them to the market. We are able to do a prototype manufacturing, but we can also manufacture parts in series production in bigger numbers. We are able to process very small parts. Smallest we had in-house was 50 microns. Please challenge us with that. But we are also able to process bigger parts where higher penetration depths are needed. If a fixture is needed to do the laser welding to position the parts under the laser beam, we can design these fixtures and you manufacture them by house with different methods, even 3D printing, which is very fast, so that we can get in production very fast. We can do post-processing for the laser welds, and of course we are able to offer you additional services for your parts that were laser welded. But we are also able to support you during development. Please get in contact with us so that you can design your part to be to make the manufacturing very efficient at the end. Okay, let's have a look at an example for a laser welding process at MeKo. This is a video of a laser welding that was done in a vacuum chamber. You see the laser beam coming from the top, hitting your device, a cylindrical device that sits on a rotating axis. And you see that there are several devices in this vacuum chamber because it's an automated process to make it more efficient. What is done there, that there's a cylindrical part with an end cap, and the end cap is welded with a laser weld around the circumference to the cylindrical part. Let's move on. We've made a sample device, especially for this webinar. Because it's a webinar, you're not able to hold it in your hands and to play around with them. You're warmly invited to visit us in Sarstedt, near Hanover in Germany, or you can visit us at the trade fair MeKo attends. You will find the dates of the next trade shows with the help of the QR code in the upper right corner. So on this slide, you see a picture of our sample device and some rendering views. On the left side, you see that the sample device consists of several components, 14 components. The lower half is made out of stainless steel, the upper half is made of nitrile, and both halves are connected with by help of a small pin with a diameter of 0.5 millimeter. And there are several welds on this device, on the sample device, that are highlighted on the right side in this picture. And there's even a very tiny marker on top of the device. I will show you some pictures in the next slides, which shows the details. Okay, here we are. On the left side, you impression how tall the sample device is. It's about 7 centimeters tall. On the upper right picture, you will see the marker device that sits on top of the nitrile part. It's a 580 micrometer tantalum marker that is welded with a flat weld to the nitrile top part. You see weldings around the circumference of the lower half, and you also see weldings around the intersection of these parts that are welded in a rectangular arrangement to each other. This joining path is more complex than all the other, and I will show you how we are able to join them in the next slide. You see the video of the welding process of the top cap to the nitrile structure. On the left side, it's an weld around the circumference of the part, and the nitrile part sits on a rotating axis which moves it underneath the laser beam. The video on the right side doesn't have the laser beam. It shows the movement of a robotic arm with the parts from the lower half fixed to it. And you need this robotic arm to be able to access the welding joint at the intersection. It's a way more complex path you need there. Okay, some other examples. On the very left picture, you see a small tantalum marker with a diameter of 70 micrometer that was welded to a stand that is not yet electropolished. The next picture shows a sphere that is welded to a wire with the weld going around the wire. The third picture shows a small tube that is equipped with an end cap that was welded to the tube, and you see that there's a very smooth surface without sharp edges. And the last picture, the fourth in the row, shows 2 metal sheets. You see the wall thickness of the metal sheets here, and these metal sheets are arranged in an X-like structure with the weld put into the root of the X. As Laura already said, we have process change. For a typical welding process change, starts with an incoming inspection of the parts, some programming, maybe a fixture has to be designed and manufactured, and sometimes the parts we get have to be cleaned before to get a clean weld. After welding, a final cleaning can take place, quality inspection, and we will pack the parts before we will ship them to you. I would like to highlight something that we do during welding and something that we can also do after welding. That's the in-process control or post-process inspection. What we use there is an optical inspection to have a look at the quality of the seam, and we can also measure details on your devices to make sure that the specifications are met. We can do a mechanical testing regarding the function of your device, of your assembly, like a pressure test or the measurement of extraction forces of marker elements. But we can also perform basic mechanical testing like tensile test strengths testing or bending test. And we can also do cross-section of the seams to perform a grain size measurement. And I would like to highlight this point, the cross-section in my next slide. There we are. You can see two pictures of a welded component with the laser weld highlighted in green on the left picture. We can use this cross-section to measure the penetration depth of the laser weld directly. We can have a look at changes in the grain structure of the laser weld, and we can have a look at the composition of the seam, of the material inside the seam via EDX, and take SEM pictures. We can inspect the heat affected zone around the weld in the base material, and we can inspect the quality of the seam inside. To be able to weld parts for you, the first thing, it's very basic, but it's very important. The joint has to be accessible to be able to do laser welding. If you would like us to manufacture parts, we need a drawing with some specifications, like dimensions, surface requirements, which material has to be used, are there any mechanical properties. We can order the material for you, we can manufacture parts for you, but you can also send parts to us for the laser welding. And if there are any requirements for the laser weld, for your components after laser welding, please get in contact with us. I would like to wrap up the webinar. For us, laser welding is highly suitable to join microscale components. It's able to do clean joints. It's an accurate process and it's consistent, and it's proven for high quality and high reproducibility.
Additionally, as you've seen today on the slides and during the presentation from Roman, MeKo is a reliable partner, and we have a very deep laser welding expertise. It's also that for over 30 years of our existence now, we are driven by innovation and precision, and so we are ready to support your microassembly challenge. This brings us to the end of today's webinar, and if you didn't get a chance to ask your question, or if something comes up to your mind later on, you can reach us by email, LinkedIn, or through your usual contact. We gather your questions, even though when they come later on, for an FAQ on our website and provide written answers. A big thank you again to Roman for sharing his expertise today, and to all of you for joining and taking part. The recording, including all slides, will be available on our homepage shortly, and we'd love to stay in touch, and we hope to hear from you again soon. Have a great day.
Thank you.